Hello guys, good afternoon. Yesterday we have solved some numericals on the thin cylinder. Today we will going on the thick cylinder. Today we will complete the theory of the thick cylinder. You know, in the first lecture we have seen when a cylinder is subjected to a very high pressure, the thickness of the cylinder wall must be very large. Thick cylinder means if the ratio of the inner diameter of the cylinder to its wall thickness is less than 20, that is di by t is less than or equal to 20, the cylinder is considered to be thick cylinder. We have seen some example of the thick cylinder: hydraulic cylinder, high pressure pipe, gun barrel, receivers, etc. Okay. Then do you know the difference between the thick cylinder and thin cylinder? Okay. First, if you ask in the examination the difference between thin cylinder and thick cylinder, then write point wise. Remember the parameters. Okay, first parameter is a definition. You know the definition of the thin cylinder and thick cylinder. For thin cylinder, the ratio of di by t is greater than 20, and thick cylinder, the ratio of di by t is less than 20. Then second parameter is a radial stress. Radial stress is very small in the thin cylinder, that's why we are neglected. Okay, but if you think about the thick cylinder, the radial stress is of significant, they have some magnitude and hence cannot be neglected. Then third parameter is a circumferential stress. Circumferential stress is uniformly distributed over the cylinder wall thickness. Already we have seen in the thin cylinder. And if you seen in the thick cylinder, circumferential stress is not uniformly distributed over the cylindrical wall thickness. And number 4 parameter, you can write different example for the thin cylinder and thick cylinder. In the thin cylinder, low pressure boiler, storage tank and receivers, etc. Okay, and thick cylinder, hydraulic cylinder, high pressure pipes, gun barrel, reactors, etc. Okay, remember that sometimes in the end sem examination you will get the question difference between thick cylinder and thin cylinder. Then write that difference with the help of different parameters. The next bit is the thick cylinder subjected to internal and external pressure. Both pressure, internal pressure as well as external pressure. When the thick cylinder is subjected to the pressure, there are different stresses are induced in the thick cylinder. First is a circumferential stress. It is also known as tangential or hoop stress. It is denoted by sigma t. Second is a radial stress. It is denoted by the sigma r. And third is a longitudinal stress. It is also called as a axial stress. Okay, it is denoted by the sigma l. I have drawn one figure. This figure shows a thick cylinder subjected to both internal as well as external pressures. Okay, in the first figure, see, I have shown internal as well as external pressure. And in the second figure, I have considered one elemental ring of the thick cylinder of radius r, small r, and radial thickness of that elemental ring I have considered dr, shown in second figure. Okay, let's see what is mean by PI. PI is the internal pressure. The unit of that internal pressure, Newton per mm square. PO is the external pressure. Unit is Newton per mm square. Di is the internal diameter of the cylinder. This value is given in mm. And DO is the outer diameter of the cylinder. This value is given also in mm. L is the length of the cylinder, given in mm. Sigma R is the radial stress. At radius R, we are consider that elemental ring. That's elemental ring having the radius R. This value is given Newton per mm square or MPa. Sigma T is the circumferential stress or tangential or hoop stress. It is denoted by the sigma T. Okay. Stress at again radius R, Newton per mm square. And sigma L is the longitudinal or axial stress. There is a one derivation is given. With the help of that derivation, we want to find out circumferential stress, radial stress and longitudinal stress. But as per the syllabus, there is a no derivation is given. Okay, or no, not required to solve that derivation. That's why you should remember the formulas only. Okay, how to solve this? You can equilibrium of vertical forces acting the half portion of the ring. We are consider the half portion of the ring. You can find out that value with the help of half portion of the ring. Then second is longitudinal strain in cylinder. Already we have studied the strength of material subject. You know how to calculate the longitudinal strain in the cylinder. Okay, if you have considered the three-dimensional body, for that three-dimensional body we have find out already that things in the SOM subject. Then determination of the sigma R and sigma T value. Okay, when you subtracting or adding some value in some equations, then you will get the some constant. Okay, you should find out that constant value with the help of the different formulas, and finally you will get the expression for radial and circumferential stress. Which equation you will get, we will see. I will shift that photo here, video. Sigma R is equal to Pi di square minus Po do square divided by do square minus di square, plus Po minus Pi into di square do square divided by 4 do square minus di square into 1 by r square. This is for radial stress. And tangential stress, sigma T is equal to Pi di square minus Po do square divided by do square minus di square, minus Po minus Pi di square do square divided by 4 do square minus di square into 1 by r square. Okay, if you have checked both equation, radial stresses and tangential stress, here is the only symbol is change. Plus is replaced by negative symbol, or positive symbol is replaced by the negative symbol. Remember that two equation. When you solving the numerical on that thick cylinder, then we needed that two equation, sigma R and sigma T. Then next, sometimes you will get the thick cylinder subjected to the internal pressure. This was asked May 15 and May 18 for 6 mark and 8 marks. Okay, circumferential and radial stresses. How to calculate that circumferential and radial stresses again? I have drawn here two different figures. Cylinder subjected to the internal pressure, see in the first figure, and second figure I have shown distribution of circumferential and radial stress. Distribution of circumferential and radial stress. Here I have distributed that circumferential and radial stress. Here I have drawn one symbol. Circumferential stress or tangential stress, you will get the positive, and radial stress you will get the negative. And pressure on the outside wall of the cylinder PO is equal to, we are consider the 0. Then we know that two equation, sigma T is equal to A minus B divided by R square. This is the equation A, and sigma R is equal to A plus B divided by R square. This is the equation B. This A and B are the constant. Okay, A and B are the constant. This A and B are evaluated from the using some boundary conditions. Okay, which boundary condition? At R is equal to di by 2. Internal diameter of the cylinder divided by 2. If you have put this in that equation, then you will get the sigma R is equal to minus Pi. And second boundary condition, R is equal to dO by 2. Then you will get the sigma R is equal to 0. I will write here equation number C. Then what we will do, substituting equation C in equation B. Then you will get minus Pi is equal to A plus B divided by R square. And if you solve this, minus Pi is equal to A plus 4B di square. I will write the equation number D. Then next slide. And 0 is equal to A plus 4B divided by dO square. This is the equation number E. Then I will do the subtracting equation E from D. Then we will get, check that, minus Pi is equal to 4B into 1 divided by di square minus dO, 1 divided by dO square. If you are solving this equation, then you will get the new equation B is equal to minus Pi di square dO square divided by 4 into bracket dO square minus di square. This is the equation number F. Then I will do the subtracting equation number F in equation number E. Then you will get the A is equal to Pi di square dO square minus di square. Okay, this is the equation number G. Substituting the value of B and A from equation F and G in equation A and B, we get, what we will get, sigma T is equal to, before that slide we have seen that same equation, sigma T is equal to Pi di square divided by dO square minus di square plus Pi di square dO square divided by 4 into dO square minus di square into 1 by R square. This is the equation number H. And sigma R is equal to Pi di square divided by dO square minus di square minus Pi di square dO square divided by 4 into bracket 4 into dO square minus di square into 1 divided by R square. This is the equation number I. Then see circumferential and radial stresses at radius R. At radius R, remember that this R. Then you will get, I will again simplify that equation. Sigma T is equal to Pi di square dO square minus di square. I will take the common outside. The remaining thing I will write in bracket 1 plus dO divided by 2 bracket square divided by R square. This is the equation 1. And sigma R is equal to Pi di square divided by dO square minus di square. I will take common outside, and remaining thing is bracket 1 minus dO divided by 2 square divided by r square. This is the equation number 2. We have find out the two stresses, right? We have find out the two stresses, circumferential stress and radial stress. Then remaining one is longitudinal stress. Longitudinal stress, sigma L. The third principal stress, that is the longitudinal stress, sigma L, is assumed to be uniform over the wall thickness of the cylinder. This stress is a uniform over the wall thickness of the cylinder. In thin cylinder also we have the assumption. Similar way, here is a one assumption. You should remember that assumption. Here uniform over the cylinder wall thickness, this stress. The longitudinal stress is in use only in the closed cylinder. We are using that longitudinal stress only the closed cylinder. Okay. Then again considering here, we are considering the equilibrium of forces in the axial direction or longitudinal direction. Then you will get pi into pi by 4 into di square is equal to sigma L into pi by 4 do square minus di square. Okay, you know that how to calculate the area for the hollow cylinder. Yes, we are consider the outside diameter minus inside diameter. Then you will get the sigma L is equal to pi di square divided by do square minus di square. This is the equation number 3. Then next we will summarize that equations. Principal stresses at the inner and outer surface of the thick cylinder, both. If the inner and outer surface of the thick cylinder, then at inner surface of the cylinder, what is the radius? R is equal to, we are consider di by 2, internal diameter divided by 2. And outer surface of the cylinder, we are consider the radius do by 2. Remember that this is very important when you solving the problem. Then choose the r value is correctly when you choose the inner surface and outer surface. Okay, from that three equation 1 2 3, the principal stresses at the inner surface and outer surface of the cylinder subjected to the internal pressures. Okay, internal pressures are summarized in the given below table. Okay, principal stress first is at inner surface, at outer surface. Then circumferential stress sigma t pi into do square plus di square divided by do square minus di square. Okay, and at the outer surface 2 pi di square do square minus di square. Then radial stress sigma r minus pi at the inner surface, and at the outer surface you will get the 0 value. Then longitudinal stress sigma L you will get at inner surface pi di square divided by do square minus di square, and pi di square do square minus di square at the outer surface. The next slide. Principal stresses used in design of thick cylinder subjected to the internal pressure. The variation of the principal stresses sigma t and sigma r across the thickness of the cylinder wall is shown in this figure. We have see in this figure is second distribution of circumferential and radial stresses, and we have seen this table. Okay, from that this table it is seen that the principal stresses are significant. Okay, the principal stresses are significant at the inner surface as compared to the outer surface. Hence the design of the thick cylinder is based on the three principal stresses: inner surface, that is radius, this is very important, r is equal to di by 2, di by 2. Therefore the principal stresses used in the design are sigma t is equal to pi do square plus di square divided by do square minus di square. It is also called as a maximum principal stress. maximum principal stress, and sigma r is equal to minus pi. This is also called as a minimum principal stress. And next is a sigma L is equal to pi di square divided by do square minus di square. This is the equation number 6. Sigma L is equal to design of thick cylinder subjected to the internal pressure. As the thick cylinder are subjected to the three principal stresses, different theories of failure are used in the design of the thick cylinder subjected to the internal pressure. Remember that. The different theories of failure used in the design of the cylinder subjected to the internal pressure are, which theory is used? There are four theories of failure is used for the design of the thick cylinder subjected to the internal pressure. Only internal pressure, not external. Design based on the maximum principal stress theory. Second, design based on the maximum principal strain theory. Design based on maximum shear stress theory. Design based on distortion energy theory. Okay, design based on the maximum principal stress theory, it is also called as a Lem's equation. Okay, sometimes in the examination you will get the question for 6 mark. Okay, derive the Lem's equation. Lem's equation means again design based on the maximum principal stress theory. Remember that. Okay, we will see how to solve that Lem's equation or design based on the maximum principal stress theory. Second is a design based on the maximum principal strain theory. Okay, we are using the Clapeyron's equation and Branch equation. Okay, for that theory, second strain theory. There are again two conditions: cylinder with closed end, then which theory is used, and cylinder with open end, which theory is used. And third is a design based on the maximum shear stress theory, design based on the distortion energy theory. All theories of failure already you have learned in the SOM subject, strength of material subject, theories of elastic failure in the last unit of the strength of material subject. But we'll take again in the next lecture. Today we'll stop here. Thank you guys.